All right, now let's look at one example where we have to use spherical coordinates. So next example, with spherical coordinates. So let f of x and y and z again equals minus yz and xz and z squared. So this is our vector field. And S is the upper hemisphere. X squared plus y squared plus z squared equals 1, with z bigger than or equal to 0. And boundary of S, again, the unit circle in xy plane. XY plane, x squared plus y squared equals 1, with z equals 0. So let's calculate again left-hand side and right-hand side here. So let's this time start with the right-hand side. Right-hand side, we need curl of f. So this is determinant ijk, d to dx, d to dy, d to dz, minus yz, xz, and z squared. So this becomes minus xi minus yj plus 2zk. Calculate. The answer will look like this. And now to calculate NDS, because we need curl f dot NDS. So NDS in this case will be R phi cross R theta d phi d theta. So we want to use the spherical coordinates. In spherical coordinates. So what are the values of x, y, and z in spherical coordinates? X will be sine phi cos theta. Y will be sine phi sine theta. And z will be cos phi, with theta between 0 to 2 pi, phi between 0 to pi half. Because we are focusing on upper hemisphere, phi will be, we change from 0 to pi half. If you want to cover the whole sphere, then phi will change between 0 to pi. So then if we calculate r phi cross r theta, what will be r phi? R phi will be minus derivative of sine phi is cos phi, so cos phi cos theta, and then cos phi sine theta minus sine phi. And similarly, you can calculate r theta will be minus sine phi sine theta, and this was sine phi, sorry. And then and then sine phi cos theta, and minus, and derivative of sine and cos phi respect to theta is 0. So this becomes 0. So then r phi cross r theta would be determinant ijk cos phi cos theta cos phi sine theta minus sine phi minus sine phi sine theta sine phi cos theta and 0. So if we calculate this becomes sine squared phi cos theta So we can continue calculating in XY coordinate, XYZ coordinate, but it's easier, I think, because right now we have sine squared phi cos theta, and then in IJK. But if we calculate this in spherical coordinates, it would be easier. So let's see how we can calculate in spherical coordinates. Or because we already are halfway through, so let me continue this in IJK coordinate, and then we can try to connect it with spherical coordinates. So right now, I'm just calculating this determinant. I got sine squared phi cos theta I, and then minus for J coordinate will be this times 0, which is 0. And then we will get sine squared phi sine theta phi sine theta J. There'll be my extra minus here. Because with 0 minus and 2 minus here, 3 minus in total, we'll have extra minus J. And for K coordinate, we'll have plus sine phi cos phi cos squared theta plus sine phi cos phi sine squared theta K. Now, if you simplify this, we'll get sine squared phi cos theta I plus sine squared phi sine theta J. And then cos squared plus sine squared is 1. So plus sine phi cos phi K. Now, there is a sine phi factor, common factor of sine phi. We can factor sine phi out times sine phi cos theta I plus sine phi sine theta J, and then plus cos phi K. Now, what is this? Look at the original vector R that we had. So if we compare it with the vector R is X, Y, Z. So this is R sine phi cos theta, R sine phi sine theta, and R cos phi. So compare it with this one. It's basically same vector, but without factor of R. So this one here that appeared here, this vector that appeared here is R, vector R divided by magnitude of R, which is just denoted by R with no vector notation. And another notation for this is R hat, R hat, the unit vector in the radial unit vector. So when you compare these two, sine phi cos theta I, sine phi sine theta j, and cos phi k, it exactly matches the vector R, but without the extra factor R. So that means this is vector R divided by its magnitude, which is same as unit vector R. So then this becomes R hat sine phi. So this is what we got by doing this cross product. Now, if we substitute back into this formula to find NDS, we can say that NDS, so in our case, we can say that NDS equals R hat sine phi d phi d theta. And what was curl of f? Now we have to do curl of f dot NDS. This was curl of f. And so we can write curl of f in terms of, because we have x, y, z, and we know the values of x, y, z. We can substitute them. And so what do we get? So curl of f. So curl of f becomes, so we had minus x, minus y, and 2z. And we knew that x was sine phi cos theta, y was sine phi sine theta, and z was cos phi. So if we substitute, we get minus sine phi cos theta, minus sine phi sine theta, and 2 cos phi. Therefore, we'll have curl of f dot r hat. So this one we have curl of f, we just wrote it above. Minus sine phi sine theta and 2 cos phi dot, and r hat we just wrote it a few minutes ago, which was vector r divided by its magnitude. So r will vanish and we will be left with sine phi. Maybe I can write it in the next line. Dot product sine phi cos theta, sine phi sine theta, and cos phi. So if we do this dot product, so we'll get minus sine squared phi cos squared theta minus sine squared phi sine squared theta plus 2 cos squared phi. So I can factor sine squared phi out, minus sine squared phi times. So then I'll have cos squared theta plus sine squared theta, which is 1, plus 2 cos squared phi. So the answer becomes minus sine squared phi plus 2 cos squared phi. So this is the dot product between curl and the vector n hat, which is in the direction of vector r hat times sine phi. N hat ds was r hat sine phi d phi d theta. And so then we just need to calculate the integral d phi d theta of this. So what was the double integral? Curl of f dot ds. So then this becomes integral 0 to 2 pi. Theta was changing between 0 to 2 pi, phi between 0 to pi half. And then the expression we just saw, it's minus sine squared phi plus 2 cos squared phi d phi. And then there was extra sine phi, remember? And hat ds we calculated earlier. This one. This one we calculated, it was r hat sine phi d phi d theta, because this part was same as r hat sine phi. So dot with r hat we already did, dot with r hat is already done, but sine phi Still, I need to, this sine phi is still an extra factor which I need to multiply with. So I need to multiply this with extra factor sine phi, and then d phi d theta. Now we can write it as two integrals. So we need which integrals do we need? Let's call it I1, for example, minus integral 0 to pi half sine cube phi d phi. So why sine cube? Because here we have sine squared phi and then extra factor sine phi outside the bracket becomes sine cube. So minus sine cube phi. So this one you can calculate just a simple math 114 integral. You can calculate this will be minus 2 over 3. And then we also need I2, which is 2 times this extra factor 2 here. Integral 0 to pi half cos squared phi sine phi d phi. So this one can be done with a simple substitution. You'll see that this is 2/3. It's a simple substitution because derivative of cos phi appears in front. You can use u equals derivative of cos phi, which is minus sine phi, appears in front. So we can use a simple substitution of u equals cos phi. And you'll see that the answer becomes 2/3. So then, therefore, the integral will be integral 0 to 2 pi minus 2/3 plus 2/3 d theta. Integrand of 0 is 0. Right-hand side becomes 0. Now let's calculate the left-hand side. Left-hand side, we had boundary of S. We can parameterize as R of t equals cos t and sine t and 0. Again, with t changing between 0 to 2 pi. And calculate f of R of t dot R prime of t dt. So f of R of t, so what was f? Let's go back. So f was minus yz, xz, and z squared. But z is 0 here for parameterization of R. Z is 0 because z is cos t sine t and 0. Z is 0. So because all three coordinates of f contain 0 and 0 is 0, sorry, contains z and z is 0. So all coordinates of f on R on the curve on the boundary becomes 0. So in other words, f of R of t becomes 0. So this becomes integral 0 to 2 pi 0 dot R prime of t dt, and this is 0. Therefore, we show that left-hand side equals right-hand side equals 0. All right, so we saw the Stokes theorem, the statement, and the connection with FDC and Green's theorem, and some examples. And in the examples, we verified the Stokes theorem either in Cartesian coordinate or spherical coordinates. We can calculate and verify that the left-hand side and right-hand side of Stokes theorem, the integral on the boundary and the flux of curl of f basically, they were the same. So we verified the theorem. Now, again, like previous topics, we're also interested in physics applications. So how can we apply Stokes theorem for some physics applications? So let's look at some applications here. Applications in physics. So first application we want to look at is in electromagnetism and Faraday's law of induction. Faraday's law of induction. So what does it tell us in differential form? It states that curl of E equals minus d to dt of B. So now if you apply the Stokes theorem, apply Stokes theorem, then we get integral E dot ds, E dot dr, sorry, E dot dr on S. So what is this? This will be integral curl of E dot n ds. Now curl of E, we can replace it here. So on C, this is on C, this is on S. So then double integral minus dB to dt dot n ds. But how can we simplify this? So to simplify, we want to use a theorem so that we can basically move this differential from d to dt. I want to move it outside the integral. So let's see how we can do that. So basically that is called differentiation, so theorem. So to simplify right-hand side, use differentiation under the integral sign for fixed domains. Fixed domains theorem, which says if B of R and T is a vector field over a fixed smooth surface S, surface S in R3, and if B is continuously differentiable in time t and space r, and if, so another condition is that the surface S should not change with time. And if the surface S does not change with time, then we can say that the double integral of partial derivative b respect to t dot ds equals d to dt of double integral b of r and t dot ds. So that's why it's called differentiation under the integral sign. So in the left-hand side, differentiation occurs under the integral sign, but then it allows us, this theorem allows us to take the differentiation outside as long as the surface S does not change with time. And also we have proper condition or assumption on differentiability of B, which has to be continuously differentiable in terms of the variables R and T. So using this theorem, the above reduces to what does it become? So we were here. So integral E dot dr becomes so the right hand side there was extra minus, and then this one we could take it out. So minus d to dt of integral b dot nds. Now b dot nds is the flux. So we can also interpret this, but it's d to dt of flux, the rate of change of flux. So right hand side becomes rate of change of flux. And left hand side, we can say that basically it's the electromotive force. So the interpretation is the electromotive force around a closed loop. So a closed loop. So left-hand side is the line integral around a closed loop is equal to the rate of change of magnetic flux through the surface it bounds. So rate of change of, we know integral f dot ds is the flux, and this is b dot ds, so magnetic flux. D to dt of it means rate of change of this quantity, so rate of change of magnetic flux is same as the electromotive force around a closed loop. Or we can also denote this with minus d to dt of phi b. So we can also call this one phi b magnetic flux.